In this video, we're going to talk about catalysts because that's the topic that the chapter covers at this point. And prepare yourself, we're going to have a fair bit of math on this slide, but it's worth it, especially for all of you who are chemists and biochemists. You definitely need to understand catalysts. And this will lead us in the next video for Wednesday's lecture to talk about Michaelis-Menten kinetics, which are the most common kinetics used for enzymes. But of course, you can't talk about enzymes without talking about generic catalysts. So this plot should look fairly familiar to you. We've got the reaction coordinates, again, along this axis, and we've got some sort of energy along this axis. And on the left side, we've got the reactants, which must cross an energy barrier in order to become the products. And as I told you earlier, a catalyst lowers the energy barrier and effectively increasing the rate of the reaction. Notice that the catalyst is not changing the thermodynamics of this reaction, which is described by delta H. The delta H, delta G, delta S are not affected by catalysts. It is merely the kinetic quantities that are affected by a catalyst. Okay, so the most common type of catalytic reaction that we'll see, especially in biochemistry, is we'll have some substrate interacting with the catalyst, and then there's going to be an equilibrium again with a rate 1 and minus 1, and then there's the substrate catalyst complex, and then that is going to produce the product and recycle the catalyst back at a rate constant of K2. So this looks very similar to what we saw on the last slide with the pre-equilibrium approximation. So let's write down our expression for the rate and begin working towards a rate law. So the rate of our reaction, change of concentration of the products with time, is going to be K2 times that concentration of the encounter complex. So now in order to find that quantity, we're going to get the rate of formation of the encounter complex. And the encounter complex can be formed from that first step by combining a substrate and a catalyst. And then it can be unformed by going that first step backwards, and it's going to depend on the concentration of the catalyst itself. Or the reaction can go through the second step and depend on the concentration of that catalyst. And then we're going to use the steady state approximation again and say that this encounter complex does not accumulate to any great degree, so we'll just set that equal to 0. So now we're going to algebraically rearrange everything. We're going to get this on one side of the equation, and then we're going to get this on one side of the equation, and then combine the concentrations of SC. And that result becomes K1, concentration of S, concentration of C, is going to equal K minus 1 plus K2 times the concentration of SC. All right? Which is going to give us a concentration of SC by dividing by both sides, K1 SC, and then down here, K minus 1 plus K2, like so. And we're going to we're not going to do that yet. We're going to take this and plug this in right there, and so we'll get a rate equals K2, K1 over K minus 1 plus K2. And then this is going to be multiplied times concentration of S, concentration of C. So all we've done is using the steady state approximation and then some algebra. We've gotten to the point now where we can define this expression here as K2 over Km times the concentration of S, concentration of C. This Km here is called the composite constant. Notice that it also appears right up here in this expression. It's this right there. That is Km. So this becomes concentration of S, concentration of C, Km, like that. And when it applies to enzymes, we will see that it has a different name, but we'll get to that in the next video. Next, we're going to formulate the rate law in terms of starting concentrations, which if you've prepared the solution, then you probably know what those are. And so that can be convenient to formulate everything in terms of those, and also this composite constant. So let's start with the starting concentration of the substrate and the starting concentration of the catalyst. Whatever the starting concentration of the substrate is, that's going to equal the later concentration of the substrate plus however much of the substrate gets occupied by the catalyst and however much gets converted to product. Similarly, the starting concentration of the catalyst is going to be whatever concentration of the catalyst there is later, plus however much of the catalyst is being occupied by the substrate. So now we rearrange these algebraically and get everything in terms of concentration of S and concentration of C. This becomes S at time 0, C at time 0, and then subtracting out these other terms here. Okay, now if we take a look up top and we see that we want to find the concentration of S times the concentration of C in our rate law expression right up here, then we're going to use what we found right up there and realize, okay, this equals concentration of SC times Km. And by filling out these values here, S times C becomes starting concentration of S minus SC minus P. Then multiply that times starting concentration of C minus SC. Okay. Now, at this point, we're going to use FOIL. Let's make that all caps, actually. Use FOIL and rearrange. And I'm not going to go through all the steps. I'm just going to give you the final result. But if you want to take a little bit of time and attempt it yourself, then be my guest. Feel free to. It's probably what I would do, to be honest, if I was first learning this stuff. It becomes starting concentration of C, starting concentration of S minus concentration of P minus SC, starting concentration of S plus starting concentration of C minus concentration of P plus that Michaelis constant, because by the way, we are bringing this part of the equation and this part of the equation to the same side and just setting that equal to 0 in the end, and then concentration of SC squared equals 0. But we're just going to assume that equals 0 because as an intermediate, its concentration is never going to get very high. So it's a small number, and when you square small numbers, you get an even smaller number, and it's negligible under most circumstances. But now we are going to find that concentration of the intermediate, and it's going to be a fraction of starting substrate concentration times the catalyst concentration, starting concentration of S, plus starting concentration of C, plus Km, like that, the composite constant. And so now we're ready to plug this right into our expression for the rate. This becomes the change in the product concentration with time, which is the rate, just equals K2, concentration of S starting, concentration of C starting, and just that whole expression plugged in there, like so, plus Km. Whew, that was a long haul. I only have a couple more things to say for this video. I'd like us to consider the situation if our catalyst concentration is far less than our substrate concentration. This is mainly going to be the case for us, especially in biological systems. Usually the catalyst is at a far lower concentration than its substrate. Then we can consider any addition of the catalyst and substrate concentrations to be negligible with respect to the catalyst. So that means everywhere we see this expression, we're just going to replace it with that right there. And so when we go back to this one right here, what do we get? We get a rate equal to K2, concentration of S, concentration of C, over S0 plus Km. And this is what we're going to be using for the Michaelis-Menten kinetics. Okay, final thing. If the starting concentration of S is much higher than that composite constant, then what that means is now this one goes away too, and the rate just becomes K2 starting concentration of S, concentration of C, divided by starting concentration of S. Those cancel out. K2, C, 0. Make that 0 a little bit nicer. This situation occurs early in the reaction, where presumably that substrate concentration is very high. And this is actually where we have a maximum rate, where the reaction is going fastest. And that should make sense, because in our experience, reactions tend to go faster at first. So we can just call that R max, or rate max. This is often called Vm in the stuff we're going to be talking about later. And this just equals K2 concentration of C, like that. And that's it for catalysts. In the next video, we'll see Michaelis-Menten kinetics.